Welcome back to the deep dive. Okay, picture this. A nation spread across over 1,000 stunning coral islands. But here's the thing. The average height, the maximum height on average, is just 2 meters above sea level. 2 meters.
It's incredibly vulnerable, hard to even imagine.
Right. And this nation, the Maldives, isn't just dealing with, the immediate threat of rising seas. They've set this hugely ambitious goal, net zero emissions by 2030.
2030, that's way ahead of the curve compared to many larger nations aiming for 2050.
Exactly. So the challenge and what we're diving into today is massive. How do you actually power an entire country with 100% clean energy when you have practically zero land for big solar farms or wind turbines?
It's an enormous constraint that really
Yeah.
forces innovation, making them look towards the ocean itself for solutions, not just as a threat.
Precisely. So today we're taking a deep dive into a really crucial piece of analysis. Future role of ocean thermal energy converter in a 100% renewable energy system on the case of the Maldives. Our mission really is to unpack how ocean thermal energy converters OTEC could fit into the Maldives' energy future. We'll look at the potential, sure, but also the surprising economic challenges and benefits, and critically, how it impacts the whole energy system. It's all based on this one comprehensive study.
It really is comprehensive. It gives us a very detailed look at the mix of technologies needed when you're facing these kinds of unique geographical limits.
Yeah.
Trying to build a sustainable energy system.
Okay, so let's start with the core problem. The Maldives' energy situation right now, or at least very recently, we're talking about a country that back in 2017 was almost completely dependent on liquid fuel.
Mostly diesel, right?
Yeah, diesel.
Yeah.
Powering nearly 270 megawatts of engines just for electricity, plus all the fuel needed for transport between those islands.
And with that coral geography and tiny elevation, putting up huge solar farms or wind turbines on land is, it's just not feasible.
You can't pave over paradise, can you? Especially when the sea might take it back soon.
That land scarcity is really the crux of it. And it's something many small island nations, SIDs, face. They just don't have the land to spare for big energy projects.
Which forces them offshore.
Exactly. They have to look to the ocean.
And they're serious about it with that 2030 net zero goal. I mean, that's intense pressure to find solutions now. The study builds on earlier work, doesn't it? Stuff that looked at floating solar and wave power.
That's right. Offshore floating PV and wave energy showed promise. And now OTEC is coming into the picture as another option, one that's getting more research attention.
So OTEC, ocean thermal energy conversion. Can you give us the quick explanation of how it works?
Sure. The basic idea is pretty neat, actually. It uses the temperature difference between the warm ocean surface water and the cold water found much deeper down. You harness that natural temperature gradient to generate electricity.
And for places near the equator, like the Maldives, that's a big advantage.
A huge advantage. You've got consistently warm surface water pretty much year-round. So unlike solar or wind, it offers a potentially stable 247 power source. That's the promise anyway.
Okay, now this study we're focusing on, future role of ocean thermal energy converter.
Ooh, it took a pretty novel approach, didn't it? Not just looking at OTEC by itself.
Exactly, that's what makes it interesting. They used what's called a structured sensitivity analysis. First time for the Maldives energy system, apparently. What that means is they weren't just asking what's the absolute cheapest mix. They deliberately forced different amounts of OTEC capacity into the system models to see what happened.
To see the ripple effects.
Precisely. How does adding OTEC change the need for other renewables? For storage? What does it do to the overall system costs? They looked at everything with hourly detail, power, heat, and transport.
And they considered different future scenarios, too.
Yeah, two main types. One where the Maldives imports synthetic fuels, or e-fuels.
Made with renewable electricity elsewhere. All right. And another scenario where they actually produce those e-fuels domestically, using their own renewable power. And they looked at both 2030, the big target year, and out to 2050 for a longer view.
So the goal was really to understand OTEC's systemic value. Not just its own cost, but how it influences everything else: storage needs, total costs, the levelized cost of final energy, LCOE, levelized cost of electricity, LCOE.
Exactly. What role does it really play when you look at the whole picture?
All right, so they did all this complex modeling, forcing OTEC in. What was the first big takeaway when they looked at scenarios purely optimized for cost? Did OTEC jump out as the winner?
Well, this might be a bit surprising, but initially, no. This study found OTEC actually plays a, quote, limited role in those purely cost-optimized scenarios.
Limited. After talking about its stability and suitability, why?
It basically comes down to competition, specifically from offshore floating solar PV. The projected costs for floating solar, especially looking out towards 2050, just get incredibly low. So low that it becomes really, really hard for OTEC to compete purely on the price per megawatt hour generated.
Okay, can you give us an example from the study, say for 2030?
Sure. So in 2030, if they're importing e-fuels, OTEC actually does pretty well in the cost-optimized mix, about 240 megawatts installed. It beats floating PV in that specific case.
Okay, so it can compete under some conditions.
Yes. But if you switch to the 2030 scenario where they produce e-fuels domestically, OTEC's role just plummets
Yeah.
down to less than 60 megawatts.
Wow. And what takes its place?
Offshore floating solar, massively, almost 2.8 gigawatts. That's, nearly 2,800 megawatts. A huge difference in scale.
Okay, why the massive swing? Why does making e-fuels at home favor solar so much over OTEC?
It's about flexibility. When you're making e-fuels domestically, you need a lot of electricity for the electrolyzers that produce hydrogen. And those electrolyzers can be turned up or down relatively easily. They act as flexible demand.
Ah, so they can soak up cheap solar power when the sun's shining?
Exactly. They can ramp up production when solar PV is pumping out cheap electricity. This makes the combination of cheap solar and flexible electrolyzers really economical. Plus, storing energy as hydrogen for later use is projected to become cheaper than storing huge amounts of electricity in batteries for balancing supply and demand over longer periods.
So the electrolyzers plus hydrogen storage give the system the flexibility it needs, making the stable but potentially pricier OTEC less essential in that cost-only view.
Pretty much, yeah. In that specific scenario, focused only on the lowest cost.
And looking further out to 2050, does OTEC make a comeback in the cost-optimized models?
According to this study's projections.
No.
No. By 2050, the expected cost drops for solar PV, batteries, and electrolyzers are so significant that OTEC is completely absent from the least cost solutions in both the import and the domestic production scenarios.
It's just offshore floating solar taking over.
Overwhelmingly, over 3 gigawatts is importing e-fuels and a massive 6.7 gigawatts if producing them domestically. Solar just dominates on a pure cost basis by then, according to these projections.
Okay, so if OTEC isn't the winner on pure upfront cost optimization, where does its real value lie? Because the study clearly suggests it does have value. There's got to be a but here.
There absolutely is a but, and it's a crucial one. This is where we need to look beyond just the LCOE, the generation costs, and think about the whole system. OTEC's undeniable value really comes through when you consider things like stability and, importantly, reducing the need for energy storage.
Ah, the storage angle.
Yeah.
Because OTEC is stable, 247 power.
Exactly. It provides that year-round, consistent electricity generation. And that fundamentally changes how much storage the system needs, both short-term batteries and longer-term storage like hydrogen, for balancing the grid. The study was very clear. Scenarios without OTEC consistently require the largest amounts of energy storage.
Which adds significant cost and complexity to the system, right? Storage isn't free.
Not at all. Less storage means less infrastructure, potentially lower overall system costs, and maybe a less complex grid to manage. It's a huge potential benefit.
Can you give some specific examples from the study on how OTEC reduced storage needs?
Yeah, let's see. In the 2030 domestic e-fuel production case, the study found that if you included 500 megawatts or more of OTEC, you didn't need any stationary batteries for short-term balancing.
None at all.
None. And the need for hydrogen storage, specifically for power balancing, disappeared once you hit 400 megawatts or more of OTEC in that same scenario.
So OTEC is effectively acting as this constant baseline, smoothing things out.
That's a great way to put it. It provides that steady foundation, reducing the peaks and troughs you get with variable renewables like solar, which is super important for the Maldives, especially with their monsoon season.
Right. The monsoons would hit solar output significantly.
Definitely. The study mentions hydrogen storage acting as a seasonal buffer for that. But OTEC, being consistent, helps smooth out that seasonal variation too, making the whole system more reliable year-round.
Okay, that makes sense. So even if OTEC itself might cost a bit more per unit of energy generated compared to projected solar costs, its stability saves money elsewhere, particularly on storage. Does this mean the total system cost doesn't actually go up much when you add OTEC?
That's another really interesting finding. The study showed that adding OTEC kept the total annual system cost and the overall cost of energy, LCOV and LCOE, remarkably stable. Even when they forced quite large amounts of OTEC into the mix, the cost increase was surprisingly small.
Can you give a number on that?
Yeah. For example, in the 2050 e-fuel import scenario, the LCOE only went from about 49 euros per megawatt hour in the no OTEC case to just over 50 euros with 700 megawatts of OTEC forced in. a tiny increase.
And why is that? How does it compensate?
The study explains it by pointing to the reduced levelized cost of storage, LCOS. Because OTEC is stable, you need less storage, and the storage you do need gets used differently, maybe more efficiently. This saving on storage largely offsets OTEC's potentially higher generation cost compared to solar.
So it's a system-wide balancing act. You trade off slightly higher generation costs for significantly lower storage costs.
Exactly. It's thinking holistically about the entire system, not just optimizing one component in isolation.
Which leads to other strategic benefits too, I imagine, like energy security.
Absolutely. That's a huge point the study makes. Energy security and diversification. Relying only on one energy source, even a cheap one like solar, carries risks.
Like what? A really long monsoon. Or issues with the floating PV supply chain.
Could be either. Or just vulnerability to price fluctuations if you're importing fuels. Diversifying your energy sources makes the whole system more resilient. OTEC, being a completely different type of resource, adds a vital layer of that resilience and security.
Makes sense. A more robust mix. And didn't the study also mention co-benefits? Things OTEC can provide besides electricity.
Yes, and these are potentially massive for island nations. OTEC systems, particularly the pipes bringing up cold gate water, also bring up nutrient-rich water.
Nutrients? For what?
For mariculture, growing things like seaweed or shellfish, it's already being tested in places like Okinawa. Imagine sustainable seafood production powered by your energy plant.
Wow, okay.
And some types of OTEC, open cycle systems, can also produce desalinated fresh water as a byproduct.
So energy, food, and water.
Potentially, yes. It addresses what they call the water-food-energy nexus. For islands often facing water scarcity and reliant on food imports, these co-benefits add incredible value that goes way beyond just the electricity bill. It's about overall island resilience.
Okay, OTEC sounds increasingly compelling from that system perspective. But let's get back to reality for a second. You mentioned it's still pre-commercial. How realistic are these large capacities, especially by 2030?
That's a fair point, and the study acknowledges it. The large OTEC capacities modeled, particularly for 2030, are definitely theoretical investigations right now. OTEC is mostly kilowatt-scale pilots. Getting to hundreds of megawatts by 2030, or full commercial scale by 2050, as assumed in some cost projections, requires, well, the study says, strong and sustained global support.
Meaning serious investment in policy focus, like we saw with solar and wind.
Exactly. It needs that kind of push to drive down costs and scale up production, mirroring the journey other renewables have taken. It won't happen automatically.
But if it does get that support, what are the cost projections for OTEC itself? Where might the LCOE land?
The study projects it could fall significantly due to technological learning. From around 82 euros per megawatt hour in 2030 down to maybe 50 euros by 2050. Which, starts to look more competitive, especially when you factor in the system benefits like reduced storage. Those projections are broadly in line with other research on OTEC's potential.
It's also worth remembering, I guess, that the cost of solar might not fall quite as fast everywhere as projected for the Maldives. They might have specific advantages.
That's a good point the study touches on. The Maldives' location, maybe proximity to manufacturing hubs in India or China, could give them access to exceptionally low PV costs. Other more remote islands might see slower cost declines for solar and batteries. In those cases, if OTEC matures, it could potentially be more competitive even on a direct cost basis. Local context matters.
And what about the environmental footprint? We talked about land scarcity being key. OTEC obviously avoids that, but does it use a lot of ocean space?
That's another advantage, no valuable land needed. OTEC does have a lower power density than, say, floating solar. You need more ocean area per megawatt.
How much more?
The study mentions OTEC, around 1.7 milliW per square kilometer versus maybe 100 or 200 for floating PV. But even with the large OTEC capacities modeled, the total ocean area used was kept below 1.5% of the available sea area in the Maldives EEZ. And the actual footprint, the space the platforms themselves take up, is described as insignificantly low. Of course, you still need careful design for storms and to minimize impact on marine life from mooring and things like that, but the land saving is huge.
So wrapping this all up, for places like the Maldives, these small island developing states, what's the final word from this study on OTEC's role? Is it a go or no-go?
It's definitely not a simple yes or no. The conclusion is more nuanced, I'd say, is that while OTEC might not always be the absolute cheapest generation source on paper compared to projections for solar, its ability to slash storage needs, boost energy security through diversification, and offer those potentially game-changing co-benefits like water and food makes it play a potentially vital role.
So it's a strategic asset, not just another power plant.
Exactly. It's vital for diversifying their renewable options and building overall resilience. It pushes us to think beyond just the cheapest unit of electricity towards what creates the most secure, stable, and beneficial system for these vulnerable nations.
So as we wrap up our deep dive into future role of ocean thermal energy converter and of 100% renewable energy system on the case of the Maldives, it really leaves us with this fascinating paradox, doesn't it?
It certainly does.
On one hand, pure cost optimization, especially looking ahead, seems to heavily favor offshore floating solar PV thanks to those projected cost drops. But on the other hand, OTEC brings these unique qualities that steady 247 power, which drastically cuts the need for expensive energy storage and really bolsters energy security and the whole system's resilience.
It forces a broader definition of value in energy planning.
It really does. And this study makes you, the listener, consider. In this urgent push for climate solutions and energy independence, should the focus only be on the lowest immediate cost? Or is there immense value in investing in technologies like OTEC that provide stability, diversity, and those crucial co-benefits, fresh water, food potential, that are frankly invaluable for vulnerable island communities?
What will it take to actually unlock OTEC's potential on a larger scale?
And what role does global support, strategic thinking, that long-term vision play in building not just a cheap energy future, but a truly resilient one? Something to think about. Thanks for joining us on the Deep Dive. We'll see you next time.